Today what I want to talk about is how we can use implicit differentiation and this fact here to come up with what the derivative of natural log of x is. Just as a quick recap, we already talked about this last time, but the derivative of e to the x is e to the x. So what I'm going to do is start by saying the thing I really want to find the derivative of is natural log of x. But if I don't know what that derivative is, I'm going to use the inverse relationship of logs and exponentials to rewrite this equation to say e to the y is equal to x. Now I can apply implicit differentiation to both sides. So I'm going to take the derivative of both sides of this equation with respect to x. A couple of different notations for that. I kind of like this one, the d dx of both sides. I'll do the easy side first. The derivative of x with respect to x is 1. And the derivative of e to the x the derivative of e to the y with respect to x, I'm going to get e to the y, and then chain rule or implicit differentiation is going to mean that I've got to multiply by y prime, or I could also call that dy dx. Since the goal was to come up with the derivative of y, a quick rearranging here and dividing by e to the y on both sides gives me dy dx is equal to 1 over e to the y. Conveniently, I have another thing that I know e to the y is equal to. And I can replace that e to the y with x. So the thing that we're going to want to add to our list of derivatives to memorize, when I take the derivative of the natural log of x, I get 1 over x. What I would like to do is take implicit differentiation to sort of expand on these two really specific derivatives that we're going to want to memorize and expand those to be a little bit more generic. So what if I was taking the derivative of something but my base wasn't e? I had an exponential, and let's say that the base on my exponential was 5. So really my function was y equals 5 to the x. If I'm not sure what that derivative is, but I do have these two facts to work with, one of our tricks for dealing with variables in the exponent is to take the natural log of both sides so that we can use log rules to bring those variables down. So I'm going to start by taking the natural log of both sides, and on this side, when I take the natural log of 5 to the x, using our log rules, that becomes x times natural log of 5. Next up, we were trying to take a derivative, so I'm going to go ahead and take the derivative of each side using implicit differentiation. So I'm going to take the derivative with respect to x on each side here. Well, the derivative of ln of y, if we've got these memorized, should look like 1 over y times y prime or dy dx. Either notation is fine. I'm going to write it as dy dx. Now on the right-hand side, this may look messy, but we just need to remember that the natural log of 5 is a constant. So if this just said x times 3, and we took the derivative, we would get 3. Well, it says x times natural log of 5, so when we take the derivative, we're going to get natural log of 5. Next up, I want to go ahead and solve for dy dx, because that was my whole goal. And I'm going to do that by multiplying by y on each side of the equation. Here my y's are going to cancel out, and I've got dy dx is equal to natural log of 5, but I'm going to take that y and substitute in what the function was for y, and that's 5 to the x. So I've got ln of 5 times 5 to the x. Now, we can think about what this process would have looked like for any constant base for our exponential here. If this had been 3 to the x, then that 3 would have followed us through. If this had been 10 to the x, then that 10 would have followed us through. So that means that we can add to our kind of generic list of things to memorize over here when I take the derivative of something that looks like a constant to the x in our exponential, we're going to get the natural log of that constant times the constant to the x. So we've talked about the derivative of e to the x and natural log of x, and then we expanded this to include an exponential with any sort of base. I would like to talk about how I take the derivative of a log that has a different base. And this isn't so much a calculus trick as really an algebra trick and something that we should remember. So if I have log base 5 of x, there's something called the change of base formula for logs, and maybe we've forgotten it, but I'm here to remind us that if I wanted to change a log with a base of any number, and I want to change it into something in a base with natural log, that conversion looks like natural log of whatever was inside divided by natural log of the value of the base. So now, if I make that swap out, and I started off with y equals log base 5 of x, and I want to take the derivative, I'm first going to do this algebra exchange to call that the natural log of x divided by the natural log of 5. Now I'm ready to take the derivative, and I'm not going to take the derivative using quotient rule, because I'm going to remember that natural log of 5 is just a number. So I could also write this as saying 1 over natural log of 5 times natural log of x, so that when I go to take the derivative, this constant is coming along for the ride. And when I take the derivative of natural log of x, I get 1 over x. So expanding this sort of more generically, if I take the derivative of a log base b of x, this is going to turn into 1 over ln of b times 1 over x. Now that we've got our basics down for taking derivatives of natural log of x and e to the x, I want to talk about some ways that we can use the properties of logs to simplify some of our grosser looking derivatives. So I'm going to start off with something a little bit straightforward, and then we'll kick it up a notch. So if I had a function that looked like the natural log of, let's say, x squared minus 1 over the square root of x cubed. Now on the surface, if I were to go straight into taking a derivative, I know that I've got a function inside of another function, so I would end up doing some chain rule. And then on top of that, in that inside function is a quotient, which means I'd either have to rewrite it to use product rule or I'd have to use the quotient rule. However, if we pause for a second and do a little bit of algebra work first, we're going to make our lives a lot nicer for the derivative. The first thing I want to note is that when I have natural log of a divided by b, that's equivalent to the natural log of a minus the natural log of b. So I'm going to take that division and I'm going to break it up. Again, I'm not taking the derivative yet. We're just rewriting the original function to clean it up a little bit first. So I'm going to have the natural log of x squared minus 1 minus the natural log of the square root of x cubed. Unfortunately, there is no natural log rule for subtraction inside of a log. So this piece is as simple as it's going to get. But this one over here, whether I'm going to take the derivative using chain rule or think about using log rules to simplify it further, I'm going to want to rewrite that square root as a fraction exponent. And I'm going to keep writing f of x over here because I want to remind myself I haven't taken the derivative yet. We're just manipulating the original function. So that square root becomes a 1/2 exponent, which means I can kind of put that all together. the 1/2 exponent and the x cubed to call that x to the 3/2. This is a place where I can do one more log rule simplification. Because I have an exponent inside of my log, I can pop that exponent out as a coefficient in front of the log. So I'd be looking at something like natural log of x squared minus 1 minus 3/2 ln of x. This is probably as simplified as I'm going to get, so I am ready to take that derivative. Whenever I'm looking at the derivative of the natural log of something, I end up with 1 over the something, and then the chain rule says I need to multiply by the derivative of the function inside. In this case, my derivative of x squared is 2x, and the derivative of -1 would be 0. Don't have to write the 0, I'm doing it for completeness. The second piece, I'm going to have -3/2, and our derivative of natural log of x is 1 over x. If you wanted to, you could combine this into a single fraction and write that as 2x over x squared minus 1 minus 3 over 2x. What if I was asked to take the derivative of something like this? Well, standing back for a second, I see that I've got a quotient rule. I see that in the numerator of my quotient rule, I would end up with a product rule. And I know that I'm going to have at least a little bit of chain rule going on because I've got e to something that isn't exactly x. We could definitely apply the quotient rule, and within that the product rule, and within that some chain rule. Or we can use our friend natural log to give us a hand. Here's what I mean. I know that I've got natural log rules that deal with division and multiplication and exponents within natural logs. And you might be saying there are no natural logs up there, and you're right, but I'm going to put one in for us. So my first step is going to be to take the natural log of both sides. And when I take the natural log of this side, that's what's going to allow me to use some of those log rules. So the first thing that I'm going to do is to break up the division and the multiplication. So when I break up the top, that's going to become natural log of e to the 5x plus, because I've got multiplication going on right there, natural log of 3x squared minus 4x, and then minus, and that's coming from our division, the natural log of x squared plus 1. I'm going to pause for a second and see if there's anything else that we can clean up, and conveniently there is right here, because the natural log of e to the 5x, since natural log and e to the x are inverse functions, this simplifies to just be 5x. So I've got 5x plus natural log of 3x squared minus that 4x minus the natural log of x squared plus 1, and that whole thing was equal to natural log of y. So I haven't actually taken a derivative yet. All I was doing was some algebra, but my next step is to take the derivative. And because I've got y inside another function, I know that I'm going to need to take this derivative implicitly. So I'm going to take the derivative with respect to x implicitly. When I take the derivative of natural log of y, I'll get 1 over y times dy dx. And on this side, the derivative of 5x is 5. Here I've got natural log of something, so when I use that chain rule, the derivative of the something part can go in the numerator. So I'll have 1 over 3x squared minus 4x, and then the derivative of that inside, 3 times 2 would give me a 6. Subtracting 1 from the exponent, I'm just at x, and the derivative of negative 4x is negative 4. Same kind of thing back here. I'm going to have 1 over the x squared plus 1. And then chain rule says I'm going to multiply by the derivative of the inside, and the derivative of the inside here would just be 2x. Now I'm not quite done, because the goal was to find dy dx, not 1 over y times dy dx. So what I'm going to do is multiply both sides by y. I'm going to copy all of this same piece down again. So 5 plus 6x minus 4 over 3x squared minus 4x minus 2x over x squared plus 1. But instead of multiplying by y, I'm actually going to multiply by what y equaled to begin with. E to the 5x times 3x squared minus 4x all over x squared plus 1. Now this technique is called logarithmic differentiation. And if we remember it in that order, first we take the logarithm, and then we're going to do the differentiation. We've talked about how to take the derivative of e to the x, and even how to take the derivative of something that has a different constant as the base for the exponential. And now I'm going to expand that to a category of functions where I have the variable in both the base and also in the exponent. And it turns out that that idea of logarithmic differentiation is going to help us out with this one too. In general, if I've got a variable in the exponent and I don't want it to be there, natural log is usually our best friend. My first step here is to take the natural log of both sides of the equation. And then I'm going to apply our exponential rule for logs, which says if I've got something in the exponent, I can pop it down in front. So this becomes natural log of y is equal to 3x squared times natural log of x. I know it doesn't look a lot better, but it looks better enough that I know how to take the derivative of this. Because now on the right side, I just have to deal with a product rule, and on the left side, I just have a little bit of implicit differentiation. When I take the derivative of natural log of y, I'll end up with 1 over y times dy dx. On the right-hand side here, I know I have a product rule, and I always like to set up my parentheses for my product rule so that I remember I've actually got 4 pieces to put in here. On my product rule, I'm going to start by taking the derivative of the first piece. So the derivative of 3x squared is 6x times, we'll leave the second piece alone, plus, I'm going to leave the first piece alone, times the derivative of that second piece. And the derivative of natural log of x is 1 over x. The only thing I have to do now is to get that dy dx part by itself. And I'm going to do that by multiplying both sides by y. Along the way, if there's anything that I can simplify over here, I'm going to go ahead and do it. Well, 6x times natural log of x, there isn't really anything I can simplify with that. So I'll leave that as 6x natural log of x. But here, 3x squared times 1 over x, one of those x's is going to cancel out, and I'm going to end up with just a 3x. I was multiplying both sides by y, but just like with the rest of our our logarithmic differentiation, instead of multiplying by y, I'm going to multiply by the function that y was equal to. So times x to the 3x squared. And that's going to be my final answer.